why we want to do balloon observation. He explained the basics. And also, I had the talk from Circo this morning. You will see that I prepared like 20 slides and I only have 10 minutes, so luckily I can go through them fast. This is the work also of Alex, that is up there, and I guess that most of them you already know, and also the Horizon team and that project that I will explain their part here. The idea of observing meteors from in a balloon-borne platform for us is to do flux determination of meteoroids in order to understand how is the distribution of interplanetary matter within the solar system. These are the definitions that more or less we use, but you will see that always when I talk about flux density, at the end I always use flux and forget the density, but I try to stick to these standards. The method is something quite old. I took the method from Bellot-Rubio and extended it for video observation. He did for photography, I extended it to video, and also I extended it for observation from the stratosphere. So basically, what we do is, this was what was explained already by Circo. When you have a camera that observes a certain field of view, it subtends an angle, and depending where you point that angle, observes a smaller or larger area of in the meteor layer. Therefore, we do some calculations, and we call this reduced area or equivalent area. That is a number, way to standardize so we can compare different volumes, different areas of observation. And at the end, we want to maximize this because it's like maximizing the number of meteors that we can observe. Therefore, this is the Earth. Originally, the method have always the observer here, so I just added this and redo all the formulation. And also implemented the calculation for distance in large zenithal angles and the air mass calculation that gets a bit tricky below 10 degrees of elevation. If you're at sea level, when you point to the horizon, you lose 4 full magnitudes. If you point at 3 kilometers, you lose 3 magnitudes. And if you want to think that extinction is negligible, you have to go above 15 kilometers. The way to go above 15 kilometers, the easiest and the cheapest way is to go on board a balloon-borne platform. So this is the optimization analysis. Of course, you want to have the radiant height, but you cannot choose that. It depends on the place. Already Circo dealt with this topic. So I was trying to increase the geometrical area, so putting larger field of view and trying to deal if you can do still some good work if you put a terribly large field of view, and dealing with extinction. So of course you want to go close when you have the radiant in the zenith, a trade-off between meteor relative speed and pixel size. And this is the part that I was working, increase geometrical area pointing always towards the horizon, but then you get a lot of extinction. So let's go to almost to the space. So then if we take 20 kilometers of elevation as a standard flight, you see that the area is smaller because you're closest to the meteors, but at the same time you have less extinction and the meteors are brighter. You get way closer. I mean, they are 100 kilometers of distance and then you are at 20, so you reduce the distance. So Circo mentioned, these are different functions that go sometimes with the square, sometimes with different functional dependency. So this is the result comparing 0 kilometers to 20. At 0 kilometers, this is for R2. It depends on the population index, but you see that closer to the horizon is better, but not exactly at 0. But however, when you go up to 20 kilometers of elevation, the closest is the better. So we used a balloon-borne platform that was already used by the Daedalus project for outreach and technology development. And we have done these missions from 2010 to 2016. I'm presenting the data from Gemini 2016 because we had a lot of work before, and these are, after 6 years, we are getting really good data. Several constraints. We are rotating at quite high speed when we are rising, when we are falling, and sometimes we have some better data in the middle. Of course, the weight is a problem. You can lose your platform and the instruments. So not use $1 million instrument, just go to commercial off-the-shelf things. First, we started with Batek, then we went to this Sony Alpha 7S. You can talk to Alex, that I guess he brought the cameras for more technical details. And this is the campaign, the data of the campaign. These are some basic data. We had the full moon, and still we reached limiting magnitude 6. What you are going to see are real-time videos. We were getting, at normal speed, not accelerated, up to 8 meters per minute, and in 4 hours we recorded up to almost 600 hours. This is the video in YouTube, and I don't need it to get it because I'm already short of time, so you can find it. If you look for Gemini 2016, you will find it. You have 4 hours where you can see the whole mission. And I'm talking about Gemini 2016 because this is what happened in Gemini 2015. So I have no time, but later if you want me to tell you what happened, how did we end up in the ocean, and how we recovered the camera, and it was used later for Gemini 2016, I'm happy to get a beer from you after the dinner, and we can have fun with this story. But then going to the data is freely available, raw data, as from the camera. You can download it from here. It's more than 50 gigas. You can do whatever you want. Of course, we will be happy if you contact us and we can collaborate. I analyzed, I guess you can please play the video. I analyzed 10 minutes. We are going to see just, I don't know how much time do you have before the questions? Okay, so well, this is, you can see here some stars that of course right now I'm not able to recognize, but well, if this was dark, you could see, well, here I saw just a Gemini. This is real time. You can see that there is some tilt, there is some other movements. It's slowly rotating, so oh, another one here. So the processing is difficult. I was only working with the half part up in of the image because under horizon, so below 0 degrees of elevation, it's very difficult to calculate extinction and other parameters. Here a brighter one. So well, it's really nice to see.
What's the field of view?
The field of view, sorry, well, now I don't have the presentation. I had it before, but it's around 90 degrees. I don't remember, but it's 90 times 60 or something like that. Everything. You can find it, well, in my thesis and also in the presentation, but I went so fast. Oh, here another one. So you have all the videos in YouTube. You have the 556 already collected together, so you can spend 10 minutes only watching 1 meter after the other. And then going to the results, so you please go back to that. Thank you. What I did for my thesis is I didn't have time to analyze the 4 hours because just 10 minutes of video took me a month. I used a periodogram because we have a lot of sensors in the balloon, so there is some extra data from the balloon. Here you can see, I guess this is pant and this is tilt, so all the movements. And then this is the 3rd hour of mission. There was some slow rotation, so we were using this data. And this is the value that I got. It's quite low, and unfortunately there are not many, as there was full moon, there are not many other people that presented values, so we cannot say, it's still reasonable, but I would expect something more like double or something like that for comparing to previous year and at this solar longitude. So this is the value that we got, and just for future work, we would like to develop something to study also the bottom part of the image with elevation below 0, and we have a lot of data for Geminis, for Perseids that are still waiting for someone to do some software and to analyze the data. So we want you, and that's it. If you have any questions.
Time for a question then.
You register all frames of the video?
Yes, we were recording at, I guess, 30 frames per second. Alex, yeah, 30 frames per second at the maximum resolution. And yeah, at the end is over 50 gigas of data. We were recording the
But I
4
think
hours.
If you all frames register against the rotation and.
Yes, all of them. Ah, no, you mean if we were registering with, no, we did visual analysis. Because, I mean, I showed you the best clip, of course, for the video. Not all of them are that nice. This one could be registered, but we didn't have time to do it. Sorry, I didn't understand the part of registered. So not yet.
Okay, great.
Did you use internal recording or external recorder?
We used external recorder, internal, and we were recording clips of 100 seconds because you know that it has a limit of 30 seconds. So at the end, what we were doing is we were triggering the camera to take new videos every, I guess, 104 seconds. I don't know exactly why that value, but we were doing it like that. Otherwise, if you use internal recording and one single video, it stops at 30 minutes.
I know.
Yeah.
Okay, thank you, Patrick.
Okay. Thank you.
Okay, so next we have Antonio Martinez Picard using Spade for radio observations.
Good afternoon, my name is Antonio. I'm a part of the radio working group of the SIDC at the Royal Observatory of Belgium. There we are running currently 3 experiments. All of them are based on this structure here. You can see we have 2 very similar in frequency. This is the frequency chart. Callisto and Arcas take their signal from this antenna here, which is a long periodic antenna. The other one, HSRS, which goes a little further in frequency, takes the signal from the parabolic reflector, of course, in the feeder. The thing is that apparently the scientists are never happy, so they want more. And for that, we thought increase the frequency range using 2 new instruments. One is Sapphire, which is intended to cover from 1 giga till 5 giga, and the other one is going lower in frequency from 20 mega up to 80 mega. Well, let's say that, of course, my talk is about Spade. I will focus on Spade. Let's say that we want to reach this 20 megahertz properly. We want, let's say, a fair enough gain from the antenna, which we could say that is around 9 dBis. And turns out that there's a relationship. You can do a lot of math. If we want to build a parabolic reflector which has these 9 dBs and reaching the 20 megahertz, we will need to build. By the way, this dish is 6 meters in diameter. The one we will need will be at least 20 meters in diameter, which is complicated, costly, and quite difficult to maintain. So what we do, we went to France, we visit our friends, our colleagues in the Station de Radioastronomie de Nancy, and they have a very nice antenna. It's an active antenna. It's an antenna which comes with, it's an active antenna, comes with a preamplifier, which is housed here. It's very nice because it's cheap. That's very nice. And the only problem is that if you see the pattern of the antenna, the maximum gain is only 0.8 dBi, far from the value we were expecting. So what can we do about it? Well, because they are cheap, maybe we can buy many of them. And if we buy many of them, we put all together in an array. And if it's that true, we can maybe take the signal of all of them, and instead of putting a receiver in each of the antennas, we just combine all the signal and feed one. If we do this, we can get this behavior. I mean, a pattern which reached the famous 9 dBs that we were required. That's very nice, that's very cool. Indeed, this is equivalent to build this famous 20 meters diameter parabolic reflector. But there's one thing. In the case that we have before, we are pointing only to the zenith. But what happens if the signal is coming in another direction? Well, if we have a parabolic reflector, we can just turn it, right? Which is quite complicated, because then we not only need to build the parabolic reflector, but we also need a good mount, mechanics, moving parts, which are usually a headache for maintenance. Well, what can we do? Well, let's try to analyze this situation quickly, because I don't have many time. So, if we consider that the source of the signal is far away, we can think that this line here represents the waveform, which is linear. And this waveform, of course, the signal is approaching in time. And what happened if maybe you can still see the parabolic behind? This line reached all the points of the parabolic in the same time. So there's no point, and there's no problem. That's why it's oriented in that direction. But it will be quite complicated to move the ground in order to put all these antennas in that direction. So what can we do? Okay, let's say that the signal reached this point first. Excellent. We take the signal there, but not the other ones. So what if we say, okay, wait a little bit with this signal. Wait a little bit, and then the signal reached the next antenna. But still we didn't reach the last one. Well, we said, okay, wait a little bit more. So in the end, the last one, we can take the signal, and we can say, okay, now you can send me the signal. What we are saying is that we are just introducing time delays to each line. So in this case, if we do that, if we manage to do this, this is what is called a beamformer, the final result of the whole array is equivalent to the one of the parabolic reflector. I mean, we can steer the signal. Well, the thing is that with the spade, of course, that sounds beautiful, because then if we do that, we skip all the moving parts, all the mechanics, and all these headaches. But of course, as the energy cannot be destroyed, the complication cannot be destroyed. It's just transferred. Where is transferred? To the beamformer. The thing is that nowadays we have powerful computers, and that's good, because then we can use, instead of analogic receivers, we can use software-defined receivers. That means that these guys are like this device over here. They are basically very fast samplers. They just sample the signal directly received by an antenna and send a data flow to the computer. And it's in the computer by software where we can add the time delay or phase shift. So this is the definition. This is the principle in which we are going to build this instrument. Brussels is located here, and we have, because we need to choose a place to put this instrument, we have a station, a radio astronomy station in Humain. It's at the south. It's around 100 kilometers from Brussels. This is the station. We have plenty of instruments over there, and Spade will be located in that square that is there. First, we need to choose which layout where are we going to use, because these antennas are cheaper, then we can buy many of them. So we are going to buy, we already did, 8 antennas, and they are going to be in a circle, 7 of them, and 1 in the center. The final pattern is a little bit more complicated than these funny round things. It's a little more complicated, but in the end, this is the case pointing to the center, obviously. You can see that we can have the required sensitivity. Okay, we started the work. The thing is that first we needed to put exactly the points where the antennas were going to be. Running. So we start with that. Then we need to pass all the cablings. We, in the end, ended with more than ½ kilometer of cable. A lot of sand and rocks and stones. This is the final result for the labeling of the terrain, because it has to be absolutely horizontal. Of course, we need to put the antennas properly, because it turns out that the place is quite windy. So we needed to not only put it on the ground, but very, very well done. Also, we need to adapt all the connectors, blah, 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 blah. This is the final result. Here we have, this is the antenna array field. But it's not ready yet, because we don't have the beamformer ready. Nevertheless, I need to test if this thing works. And for that, what I did is taking some memories from my golden years. Forward scattering is technique which is quite easy. You can have a transmitter and receiver. They don't see each other directly, but every time a meteoroid ionizes the atmosphere, when they can receive the signal on the other side. So turns out that we have a transmitter very close by in Dours. This transmitter, which is here in this area, is exactly the transmitter used by Brahms, which transmits in 50 megahertz continuously. So I went there, I took all the preamplifiers, I installed all these things in the antennas, and I set up two computers, one with an analog receiver, an SDR, and a spectrum analyzer. Some results I want to share with you. First, I got planes. These famous S shapes are planes, not exactly me. Indeed, a lot of planes. I also got some thunderstorms. You see this interference here, completely vertical. These are just lightnings. But I also got meteors. Even underdense meteors, you can see here meteors. Some overdense meteors as well. Well, I said overdense. Bigger. Okay, that's big. Epsilons. Here we are. Here we have epsilons. Not forget, please, the baby epsilon here. See it? And even from the spectrum analyzer, I got many examples, but these are two very nice ones. If you check the theory related with underdense and overdense meteors, how they're identified, these profiles shows very much coincidence with the theory. So, yes, the instrument is not born yet, but I will say this is a very good last appointment with the obstetrician. So soon I expect to, for the next year, I see, bring in real data, real results with this video. That's it.
Yes, in fact you use a low frequency, but can you use a higher frequency?
As up to 8 megahertz is
8 megahertz.
the maximum that these SDRs are capable.
I have to ask, you have not tried to use the radar graves signal?
As I said, radar graves use 143.
Yes.
143 is not on the frequency range of these antennas. These antennas are almost deaf at that frequency range. So,
Which is the distance between transmitter and receiver?
the transmit, they are at around 80 kilometers.
80?
Yeah. That's why you see the transmitter. We receive the direct signal of the transmitter, but luckily the meters are here spreading frequency up and down.
Okay, thank you, Antonio. Okay, and the final speaker today is Maria Hajdukova with the intriguing title Spurious Meteoroid Orbits.
Thank you, and good afternoon. I'm going to talk about the influence of measurement errors and determination errors on the resulting meteoroid orbit. We want to only demonstrate how strong can be this influence and how easy it is to obtain a meteoroid orbit which is actually not real. And not only one meteoroid orbit, because now these days when we have hundreds of thousands meteoroid orbits, which is a great statistical material and very useful for many purposes. But to get a comprehensive statistic of the nature of population, of meteoroid population, we need accurate orbits, because otherwise we can get also populations which are not real, or enhancement of some kind of orbits which are not real. Or so I will just very briefly to demonstrate it. I want to say that all that work is based on an older paper of Kresak and Kresakova, who showed the influence or the effect of measurement errors in both in radiant position and in velocity in one graph, showing correlation between two quantities, which I want to introduce now. So here there are some basic equations and a basic drawing or a diagram, which are familiar to everybody of you. If you look at the elongation of the radiant from the Earth's apex, and here, And if you look at the equations, we can see that the relation between the non-atmospheric velocity or pre-atmospheric velocity or geocentric velocity and the elongation, we can use to plot diagrams for different values of semi-major axis. It looks like that. So here, here is the pre-atmospheric velocity. At the top of the scale is geocentric velocity, the scale for it. And here is the elongation from the elongation of the radian from the Earth's apex. These black curves, so all the curves represent orbit for a certain chosen value of the semi-major axis. These black orbits are, or represent orbits, these black lines represent orbits which have aphelia close to the Earth's orbit. The dotted parts are the particles which are overtaken by the Earth, and these solid lines are the particles which encounter or encountering the Earth head-on. Here, this green orbits, represent orbits for 2, 3, 5 AU, and for the infinity, it means the parabolic limit. This part is radian for hyperbolic orbits. As you already seen the data, when we put the data here, this is a picture taken from another study. You see that because of this correlation, the meteors are distributed in this very narrow zone of the diagram. And the discrimination between different kinds of orbits, it's very demanding. And it is different for different part of the diagram, which you can see on the resolution of the diagram. The most demanding is exactly here, close to the parabolic limit, or along all that part. These data are photographic meteors from the IUMDC, an old version, about 4,500 orbits. 11% of them were determined as hyperbolic. So we obtain their raw data, not after any analysis. So we see that just a really very little error in the velocity, but as well in the radiant, can transfer the orbits above the parabolic limit. And we have a population of orbits which is not real. So it is important to notice that I forgot to tell it. It's important to notice that the quite wide range of geocentric velocities of their values ultimately gives quite a relatively narrow range of the heliocentric velocities. These values are for the meteoroids with aphelia between the main belt of asteroids and the infinity, yes? So you can see that the influence is really strong. So now we did the same for video meteors. So we constructed those graphs, and the video observations we demonstrated using CAMS data, about 100,000 orbits, and more than the double amount of orbits from Edmond database. We can see that a lot of orbits are hyperbolic. And we know from other analyses that the hyperbolicity can have many reasons, but all orbits from any reasons which are hyperbolic are very rare. It means they can't be real. In this data, in the CAMS data, is a higher dispersion, but that's not a real comparison because in the Edmond data, some criteria were used to select orbits. It means, I think, these high velocity meteors here, but also the bigger dispersion, was cut off because if the velocity measured from two stations differed, I don't know, about 7%, I think, so the meteor was not excluded. So the result is that the measurement errors create an artificial population of meteorites on one hand, and on the other hand, the real hyperbolic meteors or interstellar meteors are hidden within the error bars, and you cannot, we cannot identify them. So this was the one part, one kind of orbits I wanted to talk, and now I am coming to another part. So to reveal measurement errors, you have to find the area or a place or a kind of orbits which are rare, which are not, because otherwise you cannot see them, you cannot reveal them. So now we put attention to this area here. If you see this gap, corresponds to the minimum in the velocity distribution. Okay, that's I forgot to tell, but never mind. So these are distributions of the pre-atmospheric velocity from CAMS and from the Edmond data, from the same data. And you see that the minimum here, this minimum around the velocity of 50 kilometers per second corresponds to nearly perpendicular encounters. And this is a place which is among very high precise photographic meteors, almost empty. The minimum is much lower than here. Here we just selected arbitrarily the meteors with the velocities around this value. They are the red meteors here. And we can see that to have this velocity, this entry velocity, it requires or a very high inclination, no, not high, but the inclination around 90 degrees. Here is inclination, here is perihelion distance. Or low perihelion distance orbit. These are the two possibilities which allow this orbit, this stream. And the idea about finding errors is that meteors which have velocities close to this value, around the minimum, random errors in the velocity can create a non-random bias to the data because they will work in one way for some group of meteors. We speak about the meteors with low perihelion distances, which, when we observe those, and we get a bias or dispersed or error in the velocity, which move the velocity to the gap value, the orbit will be attributed to an orbit with the low perihelion distance. So it could make an enhancement of orbits with the low perihelion. To follow that, we constructed, according to the mentioned paper, these graphs for different values of inclinations. here it is shown which values for which kind of orbit we plotted. And the data here are again the photographic data. And we can see that the meteors are distributed in these two parts, which again correspond to the two maxima from the velocity distributions. And the middle part is not so filled. Among more precise data, it is even more empty. So it looks for the video meteors. And we didn't finish this analysis. We wanted to make a simulation of that if when this happens, if we measure orbits around this velocity, if it will be contributed to the low perihelion orbits. So you can see that all the curves meet here around that value for the very low perihelion distances. So we want to continue with that, but it's not yet ready, and it's just for thinking that maybe also these kind of orbits can reveal some measurement errors or their effect on the orbits. So that's it. Thank you very much.
Okay, any questions?
If you go to radar observations, there's a radar has really strong voice.
Yeah.
When the source population. So
Yes.
going from photographic to video.
Yeah, I know. We don't have very good radar data available, so we will try to do that.
Okay, one last question, anyone? Okay, thank you, Mia. Please wait just a moment for some announcements.
It's just a very short one. So at 8 o'clock tonight there will be the EMOS General Assembly here, and I welcome you all very much to attend. It will not take long. You can ask any questions and we'll tell a little bit about the organization. So welcome there and enjoy your dinner.
Okay, so now all the posters are in the boards, and I have put the numbers for some of them that they didn't have a number or the number was hidden. So we have here the ballots. You cannot see them from them, but there are 3 boxes. This is for the photography. This is for the poster. You put in order of your preference the 3 that are the best for you. The deadline is tomorrow before we go to the excursion, and we have a box that Alejandro Sanchez has it there. So whenever you feel ready to vote, you look for him, and he's going to be around and keeping the votes. So that's it. And this I'm going. I don't know if I or leave it here and you take it. Okay. So that's it. Thank you.
Okay, I have just a few more announcements. Those who arrived for a workshop and did not pay yet at the reception desk for their room, please do that. And also at the reception room, you can pick up your anti-mosquito stools, whatever does it mean. Those who already mentioned that it has some problems with the mosquitoes in the room. And what else? General Assembly will be strictly finished by 9 p.m. because the bar will be started open. I'm just kidding. We will be somehow attracted maybe after 9 p.m. to the bar. So we'll see this during the General Assembly. Okay.
They should have 50 beers prepared.
Yeah. Okay, bon appetit for a dinner.
Arstan? Estava lendo aqui já sobre algumas técnicas de rádio monitoramento. A gente acabou, o Marcelo Domingos acabou conversando com algumas pessoas da rede Polo Nosó, e eu já estava fazendo aqui algumas atualizações de técnicas que a gente pode levar para o Brasil e reacender a cobertura em rádio monitoramento. A Abramon teve uma experiência muito produtiva, a gente chegou a ter 6 estações ativas de rádio monitoramento. Foi o país no hemisfério sul que teve mais adesão a essa cobertura de registro de meteoros por rádio, mas com o fim da TV analógica a gente perdeu os sinais de referência para esse monitoramento de meteoros. Então a gente está procurando as alternativas. Existia a possibilidade de usar os sinais de FM para fazer esse rádio monitoramento, mas aqui na IMC a gente conseguiu perceber outras perspectivas para fazer os testes assim que a gente voltar para o Brasil. É uma oportunidade esse estabelecimento desses contatos, justamente porque existe essa troca de figurinhas, essa troca de informações, e todo mundo acaba ganhando com isso, né? A ciência no Brasil acaba ganhando e mais gente pode se engajar no projeto da Abramon futuramente.
Alguém veio dar uma olhadinha aí no software?
Não, eles querem ver. O pessoal, alguns procuraram, né? O presidente da IMO procurou, a Regina Rudowski também me perguntou, mas agora vai começar o horário do jantar. Então o pessoal vai correr para o restaurante para jantar e aquele intervalozinho de tempo que a gente tem depois do jantar, o pessoal vem conversar aqui, querem ver como é que funciona, como é que foi a implementação. E eles perguntam sempre, mas quando é que vocês vão implementar outros critérios de teste? Isso aí já é um projeto que existe e o Leonardo Amaral já tem isso em mente, da necessidade de implantar mais testes, fazer testes cruzados com outros critérios de similaridade.
Beleza, então vamos lá jantar.